Select the major product of the following reaction sequence. So we're starting this reaction sequence with nitrobenzene, and we've got a series of steps that we're going to be going through here. So what we want to do is we want to make sure that at every step of the way, we're drawing the products and really paying careful attention to things like the directing effects of the substituents on the ring. So starting with an aromatic nitro group, we need to recognize that this is an electron withdrawing group. So that will actually deactivate the benzene ring towards electrophilic aromatic substitution, although it still can happen. So it's just a little bit slower than a benchmark of a reaction with benzene or a reaction with an electron donating group. But all electron withdrawing groups we want to recognize are meta-directors. And so that'll be important. That means that the incoming electrophile, which it appears is going to be chlorine, these are chlorination conditions, will be directed to go to a meta position. So the product from this first step with the chlorine and the aluminum trichloride is that we're going to add a chlorine meta to that initial nitrobenzene that we started with. So we have nitrobenzene. We have two meta positions, one here and one here. It doesn't matter where we draw the chlorine. So I'm going to draw it here. I could have just as easily put it on the other meta position and it would be the same product. So after we do that chlorination, then we want to see what we're doing in the next step. So we've got iron and HCl. And so what this is going to do, this is going to reduce the aromatic nitro. So it's going to reduce that NO2 group to an amine to NH2. And there's a few different sets of conditions that could do this. Common conditions use an active metal like iron. You might also see zinc used for this. And it'll do the same thing. So it's going to take that nitro group and reduce it to the amine. So we have the iron and the hydrochloric acid. And so this is going to give us the amines. So we see now if we're trying to chlorinate something with the amine, this is an ortho-para-director. That would not have given us the chlorine at a meta position. So doing this chlorination here allows us to access having that chlorine meta versus if we were to do it when we had the amino group on there. Okay, and then the next set of conditions here. So sodium nitrite, hydrochloric acid at 0 degrees Celsius. These are conditions to take an aromatic amine and convert it into a diazonium salt. So this will form the diazonium salt. All right, so we'll add in these conditions and we'll draw the structure of that diazonium. So this is converting that amine to a compound with a nitrogen-nitrogen triple bond. And it does have a positive charge. This is a salt with the chloride on there. And of course, we still have this chlorine at the meta position. So these arine diazonium salts, the diazonium, it makes a really good leaving group because it can leave as nitrogen gas. And we can replace this with a lot of different nucleophiles. So a set of reactions known as Sandmeyer reactions use copper-1 salts like this copper bromide. So this is going to be a Sandmeyer reaction. And the mechanism for that reaction isn't entirely understood. It does appear that the copper-1 does play an important role, but the important thing to focus on for our needs is to look at what we're replacing it with. So the ion bromide here is our nucleophile, so that bromide is going to replace that diazonium. Right? So that we end up with the chlorine and the bromine meta to each other, which is an interesting result. If we were to try to just straight do this from benzene, we would not be able to get chlorine and bromine meta because they're both ortho-para-directors. So this gives us access to a compound that we wouldn't otherwise be able to make. And in terms of selecting our response, this is the same as C.